去看一下浏览器吧。哎，回来了，哎，好。Okay, good. So let's start the second round. Come in.
I'm going to challenge number 9, magnetic.
Number 9. We would like to accept. Okay. Challenge accepted. Now start the class. You have 5 minutes to prepare. And meanwhile, please write down the names of your representatives.
Ready?
Okay, please proceed.
Hello everyone, I'm Isaac Zhang from
from Team Miracle. Today I'm going to present the problem 9 magnetic assist. The problem statement is attach one or two magnets to a non-magnetic and non-conductive base such that the strength of the magnet is different chain. Eventually, how the motion of the moving magnet depends on relevant parameters. Our quick question is: 1. How does the number of the attached magnets affect the system? And 2. What the factors influence the magnetic force? Just the force between the one magnet and two magnets. And this is our order. We are moving to observation, we are going to experiment, and the theory, and then conclusion. This is our observation. Let's observe how it moves. And we also how the magnet moves and compare its observation periods. This will slow. Wait a second. And it moves faster. The magnet on two magnets moves faster. And we know that the pendulum may swing in two directions. And we want to demonstrate the problem. And let's do the experiment. The theta is like the graph shows, and we use a baffle used to limit it into one motion to one single direction, and because we want to analyze the problem in two directions, and so we use a baffle, and we use a suspended magnet weighing 4 grams with a 17.5 centimeter string, and the fixed point of the pendulum is positioned directly above the center of the magnets or one magnet. And we let the first experiment is the balance experiment. We let the suspended magnet be balanced and with three forces: gravity, tension, and magnetic force. And we know the magnetic force is equals to the expression. And we change the position of magnet on the base, and we will observe the magnetic force. And this is our result for the experiment. And we use a preliminary experiment to observe the damping factor. We let the suspended magnet swing above no magnet. It's just swinging. And we want to observe the damping factor of the pendulum. Okay. And next one. And we did it twice, and with different amplitude initial. Sure. Next one. And we let the suspended magnet swing above one magnet, and the fixed one is above the one magnet. And we control the initial position of the magnet, and we change the height of the fixed point, and we observe the period of the pendulum. Like it. And the result is the left graph shows the time displacement relationship of the 23 centimeter height of the pendulum. It goes like this, and the height to period relationship is like a linear function. And we did similar thing that we let the suspended magnet swing above two magnets, and the fixed point is above the center of two magnets on the base, and we let the suspended magnet swing in the x direction once and many times, and we let the suspended magnet swing in z direction, and we also to control the initial phase, and we change the height of the fixed point, and we we observe the period pendulum. And the result is like that. The left graph shows the time x displacement of the pendulum, and the right result is the period of high period. 2 max x graph means the pendulum line swings in x direction, and 2 max z this means swings in z direction. That is the upper graph shows. And we get off the baffle, and we let suspended magnet swing freely above 2 magnets. And we change the height of fixed point and observe the period pendulum. We observe the x displacement and the z displacement, and it's like that. You see the value, and the height period relationship is like that. And this is our theory that this time to do math. And so let's define these parameters. H means the height of fixed point, and L means the length of string. R means the distance between suspended magnet and another base. Theta means the angle of tangent, and phi means the angle of 2 magnetic moments, and mu means the magnetic moment, and A means the radius of the magnet for the magnet is cylindrical. And we know the magnetic field of a dipole is the equation. And from the Lorentz force, we know the magnetic force, that can be demonstrated like that. And we know the force only affects at short distance, because if you put the magnet too far with a large distance, it will affect. So we can approximate this, and notice that the kappa is a constant that we determine it with our experiment. One. And the theory about the equation of pendulum. The equation is that the acceleration, the angular acceleration, and the gravity, and the resistance of air, and the magnetic force. Notice the I means the number of the magnets. It means we put 2 magnets, or we put magnets and put it, and we combine the force of it. And of course we cannot get that it is analytical expression, so we use Python to get it into the mathematical expression. And this is our data analysis. We use the experiment 1 to ensure the kappa. The kappa is about this. And the damping factor is like this. Damping factor equals to beta divided by 2 ms, and it's about this. And the beta we know is this. The blue stands for the theoretical prediction, and the orange stands for experimental result. We can see it matches. It really matches. And the other analysis 3 matches. And another. This one. It still matches. Yes. So we use Python to calculate the result and compare with our experimental result, it's always red matches. So let's go on to conclusion. We can predict the pendulum motion by the equation, and the motion of the pendulum can be decomposed into z x direct oscillation and z direct one. That's all.
Then 2 minutes for 33 questions.
Hello, Mr. Isaac. Did I pronounce it right?
What?
Your name.
I'm right.
Can you go to page 9 first?
Page 9. Okay, page 9.
Want to ask you about a question about your experimental setup.
Yeah.
So, first is that you said you suspend your magnets in the same height on the first experiment, is it?
We use the same height, right? In the first experiment, it is.
And in your experiment, all of your experiment, you measure the period of all motion of your magnets. Is that correct?
What do you mean?
Okay. So your main focus is on the period of each motion, each swing of the magnets.
Yeah.
Yes. So in your first experiment, you said that you want to find a balanced place in the systems.
Yes.
Is it you only use one magnet in it, or does it have magnets?
There are one magnet on the suspended, and there are another one magnet on the base.
What are the relation between the magnets fixed on the ground with the magnets that swing on the sky? Because I see that in
The magnet suspended to the swing because it's a balance. The balance is different.
okay. But I see here it looks like your rod have a little bit distant from the magnet. So it's like where's your in this picture? Where's the place where's your initial place in it?
What do you mean? What do you mean about the initial place?
Also, this is the balanced place, is it?
This is a better place.
So, okay, I got it. And it's please next page 6.
Next one. Oh, what one?
The next one.
Next one.
So, sorry, page 9.
Page 9. Okay.
So, why are we here has a period with heights? Because you said it's a balanced place.
That's a.
Time is up.
Oh.
Your opponent, 3 minutes to prepare. All teams, please keep your voices down.
Okay. Hello everyone, I'm from Team Crusader and from Changhua Senior High School. Today I'm going to discuss with the magnet assist with my reporters. So let's still look at the problem statement first. So attach a rope.
What's the problem?
Okay, so attach one or two magnets to a non-magnetic and non-conductive base, such as they attracted a magnet suspended from the string. Investigate the motion. So from this problem statement and also from my reports, I can see that the way he shows the motion is mainly on the period of the magnets. So I'm going to a little bit doubt on the way it, how do I say, detect the motion. So let's look at the pros and the cons first. Okay, so from the merits, so first one, I think he has a full diagram to show each period of it, and second, he tells me the process of his thinking, and also the clear mathematical derivation, great demonstration, and clear parameter of each initial state. And second, I think the main drawback I'm confusing about are his manipulation during the each experiment, because I did not really see how these magnets move during his displacements. Like I see the period are going to be shorter, but how it works, how it moves, I didn't see that. And second, I think he didn't consider the Earth magnetic field, because we know that Earth has a magnetic field also. But in his experiments, I cannot see something like the west side. He put it on the west, east side, and north, south side. And second is that the diagram on the diagram part, it's a little bit unclear on it because each point I cannot really see what it really represents. And the last one I was suggesting is to play some video to show how each magnets move on how these experiments. And the next one is the things I'm going to discuss with it. So on the theory part, I wouldn't take too much time on it because his calculation on magnetic field, so far I feel there's no problem in it. And second, he says that the motion are predictable, which a little bit violates to my prediction first. And the last one is this, at the beginning it says that if the number of the magnets increase, the speed of the suspended magnets will also increase. That's the part I'm also going to talk about. And on the experiment part, he changed the number of the magnets. He find the balance point in it. And he also used only no magnets under it, and also changing the height of each magnet suspended, and using two magnets on the previous part also. Also the data part, I think it will be a little weird to be a linear period, so I'm going to also discuss it. And he said, at the end he says that it's during his own period, it's like damping, but he also says that it speeds us during the part. So also I think it will be a little bit violated to it. The 2 points are contrary to each other, so that's the part I'm going to also ask about it. And the last one, he says that the period match his point, but I did not really see the calculation on the period, so that's also I'm going to ask about it. So that's my reports on the my report. So that's it.
First I just want to say. First I want to say the.
Sorry, I'm the opponent. Can I deliver my words first?
Okay.
So, still on the experimental setup part, I think each part has a lot more unclear part on it. So, first, can you turn to the page? Page 12.
12.
Yes.
Okay.
Page 12. So this one, what's your variable during this experiments?
For the variable, the experimental variable is the height of the fixed point, and the dependent variable is the period of the pendulum.
A period of the pendulum.
Yeah.
Can you tell me how it really swings during the reality? Like, can you draw it, or so it goes to, so it stops after time?
Yeah, because they're standing.
Oh, okay. So, but at the beginning, it's on page 3, I guess. I remember.
3?
3 or sorry, the next page 7. Here it has a video on it. I remember there's a video. Yes. So here. Okay. It seems like I see something wrong. So does each part of your experiment, all at the end of it, the magnets all stop at the middle part, or is it? Does it have a certain place that it stops, like in each experiment?
What do you mean?
Like in the wine magnets, does it stop always at this point? Because in your balance part, it looks like it's a little bit twisted.
Oh, there's something I have to explain. It is on the page 9. We should. I'm sorry for I put this. I'm sorry for I put this wrong title of axis.
Oh, sorry. What does this diagram mean? Because it's after the position with the. When does each position to be different if your displacement is the same? Like,
Okay. Can I use the board?
yes, of course.
If you want to make the picture the magnet force balance, this is the fixed point.
Yes.
And this is the magnet on the base. We know gravity is there.
Yeah. Yes.
And we know the tension is there.
Yes.
And we know the magnet force. We assume the magnet force is like that.
Oh, okay. So look, is it the force in here means the magnetic force you mean here?
Yeah.
Okay.
And we know, and because we know the angle, the phi, and the angle theta, so we can calculate and we know the y, so we can calculate the magnetic force.
Okay. So if that's the case, then what's the x position in here? Like, what's your original force? Where's the 0 to 1?
I mean the fixed point on the fixed point, the point just directly below the fixed point is the initial point 0, and the x position is like that. Is that.
Okay. Okay. And let me see more clear. But in here, it's like where's the? It's 1 centimeter. It's 1 centimeter of each magnet. How big is your magnets under it? The diameter of it.
The diameter is about 1 centimeter.
It's about 1 centimeter.
1 centimeter.
Okay, so it looks like you just move like each magnet's place during your process, is it? And
We move it. Here is in position, and we move it once.
okay, I got it. But the next question is, how is the force become sometimes bigger, sometimes shorter, sometimes bigger? Because if it really manipulate like that, I mean the theta in here will be increased. Oh, sorry. Theta in here will be increased a little bit, meaning that the gravity will maintain still, but the F in here needs to have a larger force in it. But how come it has upward and downward in here? Like, what really happens in your manipulation? Like, how do you explain the sudden growth and the sudden drop in this diagram? Like, is it just a calculation or?
We just calculate. You mean the force and
like if you move like your magnets was originally like this is your like your initial magnets is in here, then the force you are measuring will be like here. Wrong position. This is your force, and it will become like this. Then I guess this will be a little bit twisted, like maybe in here.
yeah.
So if you want to maintain this force, then how does it say that? If you want to find the balance place, then I guess the force should maybe have a trend. Like maybe when it goes to here, it may increase, or it goes to this place, it may decrease. But in this diagram, it looks like it has a increase part and decrease part. So what really happened? That's what I want to ask.
When you go with the magnet there, the magnet there, and we put the magnet on the base further and further, and the magnet further to this, and the magnet will when the distance is far and the force decrease.
Okay, I can see this trend here, but okay, I also skip this question first. So can you turn to the page 12? Still same. No. So 11. Sorry. 11 is my fault. So this is the time versus amplitude. So what do you mean by amplitude in here?
Oh, okay. We know it is t time, and it is amplitude. This is a displacement
The displacement of what?
for the pendulum of x position, and we know it goes a damping in oscillation, so we can know the displacement versus time is like that.
Yes.
And we catch these points.
Oh, okay. So you catch the highest point of each period.
Yeah.
Okay. So the following question will be like, okay. Oh, here. Why at the beginning there is a bigger than lower than bigger? I can see a lower trend in the afterward, but how come it goes higher at the beginning?
That may be the error by the tracker.
Error by tracker.
Yeah, we use tracker to catch the motion.
The motion. Okay. Okay. So I guess this may be just a failure of manipulation. And oh, sorry. What's the difference between this picture? Like, what's the different parameter?
We did twice and did the first one and the second one.
Also, so this is like a two time. Okay, I suggest you maybe you can combine this picture together.
Oh,
like
you mean
we
overlap the graph? That's the graph.
Oh, okay. So yeah, next page is page 13. Yes. Page 13. Okay. So from here, this is the damping you said, and can you turn to the experiment with two magnets, and you place it at XL. Okay. So in your experiments, how do you place the magnets? Because in my imagination, if you push the magnets like you cannot be fully precise at this picture.
You mean like this place?
Oh, sorry.
You mean like I put a magnet in the initial phase like there or there may cause different results?
Yes, that's the reference.
That's all explanation. There's the board, there's the base, and there's two magnets. The base point is above there, and we mark the point, and then we mark the point on the base, and we use hands and put the certain magnet just directly above the mark point.
So you make sure that all of your starting point will be on the same mark points?
Yes.
Okay. So is it on the, because in your z-axis it seems like it's a little bit twisted. How do I say it? It's not a 90. It doesn't look like a 90 angle on it. Like this is.
What do you mean?
Like in my perspective, in my how do I say imagination, this is like the cross should be like a straight one.
You mean why the
yeah, it's
the road-
twisted.
That may be the error of the experiment, but if you put the point, we just care about the point of our string that fixed in this point.
Time is up.
Okay, so during my
Time is
discussion.
up. Oh, sorry. You want to summarize?
Sorry. Okay, so during my discussion with my reporter, I mainly talked about how he doing his experiments on the first one.
Reporter, you may be seated. Reporter, you may be seated.
Sorry. During my discussion, I mainly talked about the force that he said that he measured on the first experiment, and how he calculates the amplitude of each diagram. And I also asked about how did it control the precise points of each magnetic assist. But I still consider that because I just quote my some references. It says that even though your hands are put in the same place, the motion of the magnets is still be chaotic because our hand cannot just be precise as to the quantum scale. So I think there will be something weird on it, but based on what I seen from his report, I think to his explanation, I mean, because I didn't see the real motion of the magnets, so I guess it will need some correction.
Okay. The reviewer.
Hello everyone, I'm the reviewer from Team Manuli, and my first question I want to ask to the reporter, and do you think the geomagnetism will affect your experiment?
You mean the what?
The magnetic field of Earth.
Yeah. The magnetic field, a magnetic field affects the forest. So.
And what do you think about geomagnetism will affect?
Yeah, I also think it will affect it, but didn't see the considerations in his experiments.
Okay. And the second question is, magnetic field will change its direction during your experiment?
You mean you mean what?
Like because your stream length is too
You mean
short,
the direction is you mean
like your
the
magnet is
distance is larger, the force is less.
your magnet is not horizontally, and because your string is too short, so maybe the magnetic field strength direction will change. About the
You mean the magnetic field will change during this experiments?
Yes.
Yes, for sure, because the magnets on the string is also swinging.
okay, and about the page 18.
Page 15.
And do you have some equation to prove that there is the linear?
We can go next to the data analysis.
So you think your model is linear, right?
Basically yes.
Okay, and how about the opponent?
It looks like linear too, but I guess use period as in the path of motion may be weird during this in this topics.
Okay, and about page 5.
Page 5. Okay.
And I see that you use pen to release the magnet,
That's a demonstration.
and so you use what to release?
I use hand to release the certain magnet on the in the experiment, but it's above the same place. So I don't think so.
Control the same height and place to release the magnet.
We control the same initial place of the magnet.
Okay, and about page 22.
Thank you. Okay.
What do you think? What affect the damping?
What affect the damping in like the force, like the air resistance and the friction of the baffle.
Okay, and how about the opponent?
I have the same points with the reporter, just like what he says.
Okay, and what do you think about what will be here?
Why it will be chaotic? Because the magnetic field in this magnetic are all
10
not
seconds.
balanced.
You have 10 seconds to answer.
Are not all balanced in the whole board. So if changing the different places, then it means that the
Okay? 10 seconds is up.
Thank you. Thank you. everyone, I'm a reviewer from Team Bernoulli, and today I'm going to review the problem number 9, magnetic assist. And for the summary of the report, it used a theory for force analysis and magnetic force and weight of the magnet, and also his experiment used different parameters like different position, different number, different height, different and suspended magnet, and he used 17.5 centimeter string to do the experiment. And about the strength of the reporter, he doing different parameters, and he also do the lab experiments, and he used and compare the difference between the experiment and the data. And about the suggestion, I think he could do more explanation to the data, and also get more quantitative theory to experiment data. And also, he can show the motion of the magnet to explain more clearly. And about the opponent strength, he asked him some detailed questions to his experience setup and also the data. And he can tell the mistakes from the report, and he understands this segment well, and also he asked him definition of symbol in the report. And about the suggestion, I think he can ask more questions from the report and also ask more about the theory, and also focus on more about the data analysis. And I think that in their discussion, there's some mixed point like mechanism of Python, theory, combination, and small error in theory and experiment. And about the discussion, the opponent asked magnet force analysis, and reporters say the magnet force and also the weight is the force they use F. And I think he will also have the damping force to explain it. And the second is damping force, and he said he used tracker error. I think he can explain more detail about it. And about the experiment, the opponent asked about the variable, and the reporter say he checked the height, and I think he can show more clear about how he do of the parameters. And second is movement, and the reporter say he tracked by base, but I think he can show the whole video to show his experiment. And about third is diagram meaning. I think a reporter say he used X amplitude, and I think he can present well. And for his size of magnet, and he said 1 centimeter, and I think he can show the setup. And about my question, I asked him, changing the direction affect magnetic field, and he said it will affect. And I think he should use more longer string to do the experiment, because if he use too short, it will affect the direction of the magnetic field. And the second, there are theory to prove it's linear, and he said according to the data. And I think he can combine the theory line, and I don't think it will be linear because the force will not within two magnets wasn't proportion to the direction. And third is what kind of damping force is, and the report say it was air resistant, and I think he can complete force analysis more. And about 2 years 3, and about kappa and his tail, I think he can tell more details about what's meaning of his picture, and also I think he could show the trajectory of the motion of the magnet. Okay, and that's all my review. Thank you.
Now it's time for questions from the viewers.
Let's moving on to the remarks.
Oh, sorry. Okay, sorry. Please.
Hey, so
You can have 10 more seconds.
this is our concluding remark. With the observations law, X position to magnetic force experiment, and we measure the force, we measure the magnetic force, and we measure the damping effect, and with blank experiment. And we did the height period experiment of 1 magnet and 2 magnets, and first constraint in the 2-dimension motion. And we did the height period experiment of 3 pendulum, just a 3-dimension motion in the experimental form. And we derived the equation of the pendulum and do the simulation with Python. And we show that the simulation matches with the experiment. The equation is And short question. The clear we put the wrong. We analyze for we put the wrong on y-axis and z-axis on the the experiment 1. And I don't think the opponent understand the experiment well. No. And about the discussion, we talk about the balance point experiment and the damping experiment, and the amplitude relationship and the release point on the magnet, but we fix it and track it to make sure in the same initial magnet. The Earth's magnetic force, of course, change, but the influence is negligible. Thank you.
Thank you. Now questions from the viewers? Do we have questions? Please.
So just ask your comments. So in this experiment, even in the presence of just a single magnet, is it possible is the pendulum swing amplitude can increase at least momentarily?
Increase what?
Amplitude.